Hi and good evening. Our group will discuss about real gas and its application. So here are the group members. The first one is Fazrul bin Jalain. The second one is Muhammad Lufi Aiman bin Muhammad Zahir. The third one is Najah Amilin binti Muhammad Anwar. And the last one is Amisha Hibria binti Ismail. So, I will start with introduction of real gas. Real gases can be defined as non-ideal gases whose molecules occupy a given amount of space and have the ability to interact with each other. Real gas is a gas that obeys gas laws at all pressure and temperature conditions. It deviates from its ideal behavior as the gas becomes huge and voluminous. True gases have velocity, mass, and volume. They liquefy when cooled to their boiling point. The space filled by gas is not small when compared to the total volume of gas. Besides, a gas must be considered as a real gas when it is approaching its condensation point. Furthermore, almost all gases must be considered as real gases as they approach their critical point. Next, this is the real gas law equation. By implicitly including the effects of molecular size and intermolecular forces, the Dutch physicist Johannes van der Waals modified the ideal gas law, which is PV equals to nRT, to explain the behavior of real gases. So we got the real gas law equation, which is P plus AN square over V square equals to V minus NB nRT, where A and B represent the empirical constant, which is unique for each gas. N square over V square represent the concentration of gas, P represent the pressure, R represent a universal gas constant, and T is the temperature.
Cryogenic liquids are liquids that deal with low temperature with their effect on matter. It is liquefied under high pressure condition and can expand to a very large volume of gas. They happen to be some of the most commonly used industrial gases that are handled, transported, and stored in the liquid state at cryogenic temperatures. There are two types of cryogenics. Firstly, inert gas, which does not burn or support combustions. Examples of this group are nitrogen, helium, and neon. The other one is flammable gas. Some cryogenic liquids produce a gas that can burn in air. The most common examples are hydrogen, methane, carbon monoxide, and liquefied natural gas. There are two characteristics of cryogenic gas. Firstly, cryogenic gases are extremely cold and small amounts of liquid can expand into very large volume of gas. Cryogenic gas often condense the moisture in air, creating a highly visible fog. Cryogenic liquids such as oxygen, nitrogen, and argon are often used in industrial and medical applications. We can see on the table below that these liquids are extremely cool and have boiling points below negative 238 Fahrenheit. In this video, we are focusing more on the application of cryogenic liquid, which is liquid nitrogens in daily life. Liquid nitrogens is one of the most commonly used cryogenic liquid. It is also a low viscosity liquid that is colorless and odorless. Nitrogen's temperature in liquid can be instantly reduced to its freezing point of negative 346 Fahrenheit by placing it inside a vacuum chamber.
The application of cryogenics in the pharmaceutical industry, particularly in freeze drying, involve understanding real gas behavior. In the freezing stage, cryogenic gas like liquid nitrogen rapidly cool the product, requiring adjustment for non-ideal gas behavior. During primary drying, sublimation occurs under low pressure, and managing deviation from ideal gas law is crucial for maintaining balance. Secondary drying removes residual water, with efficiency influenced by real gas properties. Inert gas like nitrogen create stable atmospheres to prevent oxidation, requiring knowledge of non-ideal behavior under low temperatures. Overall, incorporating real gas principles optimize freeze drying and ensure product quality.
Next, we are moving to how cryogenic in freeze drying works. First, the machine lowers the temperature in the still chamber to cryogenically freeze the material solid, separating the water content on a molecular level. This means that the freeze drying process begins by rapidly freezing the material to extremely low cryogenic temperatures, typically well below to the normal freezing point of water at 32 degrees Fahrenheit. basically separating the ice crystal from the surrounding non-aqueous components on a molecular scale. Second, once the material is frozen solid, the machine uses a powerful vacuum pump to reduce the atmospheric pressure in the chamber below 0.06 atm to enable the frozen water to undergo direct sublimation from solid ice to water vapor. This direct sublimation process is important for preserving the material's composition and structure during the drying phase. Next, while maintaining the low pressure environment, the machine applies a small amount of controlled heat to the frozen material, causes the ice to transition directly into water vapor, which is then removed from the chamber by the vacuum pump, preventing any rehydration of the drying material. Lastly, this gradual sublimation process preserves the material structure and composition, allowing the dried product to be sealed in moisture-free package for a long-term storage.